Kia ora and welcome to question 3 of the 2009 Scholl Calc exam. We've got two parts here, although part B has two parts in it. The first is on complex numbers and a common error that students make when adding fractions. The second part is also complex numbers, but more focused on the geometry of the problem. It's quite a quick question if you notice the shortcut to part B, so let's get started. Okay, an error sometimes made by students learning about complex numbers is to write the following. In other words, they don't know how fractions work. Show that it's never true for the above conditions. Okay, so we go about doing a proof by contradiction here. We try and show it works. So does this equal this for any A or B? Okay, well if it did, we could put the fractions back together on the right hand side. I'll put a question mark over that because we're testing it. IB plus A all over AIB. And then we can cross multiply. Kind of see what's going to happen here. So the left hand side is a purely imaginary complex number. Okay, it's AB times I. It doesn't have a real part. And the right hand side is a complex number that when we expand this, we get a real part. We get the A squared and we get a minus B squared out of that. And then we've got an imaginary part which is two lots of AIB. Or ABI. So for this to actually be true, that there AB would have to equal 2AB. The imaginary parts would have to be the same because that's what equals means. Complex number on the left is the same as complex number on the right. So therefore AB equals 2AB. Now that's only going to be true if one of them is 0. Only true if A equals 0 or B equals 0. But we also need this dude to be 0 because there is no real part on the left hand side. And A squared minus B squared equals 0, which is A is plus or minus B. If one of them is 0, one of A or B, then the other one has to be 0 based on this relationship. So A equals B equals 0. But that can't be true because if you go back to the original question, they rule it out. Okay, they say that the complex number can't be 0, and we know that can't be true because it's in the denominator. And if A and B equal to 0, then the whole equation is not defined. This is a contradiction because A and B can't be 0. Okay, part B gives us 6 points in the Argand diagram that are roots of a degree 6 polynomial with real coefficients. And we've got the points lying on two concentric circles around the origin. So I've done this with my class before, and it's actually similar to another scholarship paper, I think 2010. You can use geometry to find all the solutions given that the real one is K. So you can go around the diagram and you can use the fact that these are equilateral triangles. For example, this length here is K, and we can make a right angle triangle there, and we can work out all the other points. And I mean, I challenge you to do that. However, the fact that we then, once we've found the polynomial, need to differentiate the polynomial. If you think about it as 6 individual roots, you're going to have 6 brackets. How are we then going to differentiate it? We'd need the product rule on steroids? No, we need to expand the brackets and then differentiate them. We need to find a pattern and use the symmetry of the shape. Given that the real root there is K, we can find that one, and that one from the equation x cubed is equal to k cubed. Because if you think back to merit level questions in NCA complex numbers, we used de Moivre's theorem to solve a problem like that. And the first thing we do is write the problem in polar form. So it would be k cubed cis 0, because k is a real number and k cubed is a real number. And then we would cube root, so we get k cis 0 as our first solution. Our second solution would be k cis 2 pi over 3, which is the one on the top left. And our third solution would be k cis 4 pi over 3, which is the bottom left one. And they're all k away because they're all lying on a circle. Now, how do we find the ones that are on the inside? So notice that the left one in yellow there lines up. It has the same real part as the blue ones at top and bottom. So if I can use the fact that k cis 2 pi over 3 is one of the real solutions to that, one of the complex solutions to the first cubic, then finding its real part, it's pretty simple. I just expand out the cosine plus I sine part, the cis notation. And then the real part, which is the thing that lines up with the yellow solution's real part, is k cosine 2 pi over 3. Cosine 2 pi over 3 turns out to be negative a half. So that solution in there is minus k over 2. You can also prove it using geometry and right angle trig. Looking at the diagram, it seems about right. Even though diagrams usually aren't drawn to scale, that's halfway between the origin and the outside circle. And then we just think about how to solve, what equation would solve to give that as a solution and the other two. So the blue is x cubed equals k cubed. The yellow ones are going to be x cubed equals to minus k over 2 all cubed. Clearly the real solution to that equation is minus k over 2. The other two solutions will come using de Moivre's theorem. So we can tidy up that cubic if you want to, but what would the power of 6 equation look like? So using our working from the diagram, p of x will have factors of x cubed minus k cubed. That's coming from the first one, just rearranged to make it equal 0. And then if I rearrange the yellow one, I've got an 8 at the denominator, so I can write 8x cubed equals minus k cubed. And I can put that on the other side as well. Okay, so p of x equals x cubed minus k cubed times 8x cubed plus k cubed. That's a power of 6 equation. Technically speaking, we could have a constant in the front of that and it wouldn't change the solutions to the problem. And the question did ask to say list the exact roots of this equation. I've already got 3 of them when I used de Moivre's theorem to solve the x cubed equals k cubed. So let's just write those ones down. x1 equals k, x2 is k cis 2 pi over 3, and x3 was k cis 4 pi over 3, which you can write as k cis minus 2 pi over 3 as well. And then solving the other bracket equal to 0, we got the fourth solution, which was minus k over 2. The fifth solution is k over 2. Be careful, because when you write things in polar form, the modulus is always positive, and we're told k is positive. So k over 2 cis, go back to the diagram where the yellow is. It's at an angle of pi over 3, or 60 degrees. And the other one underneath is minus pi over 3. So k over 2 cis pi over 3 and k over 2 cis minus pi over 3 are our solutions. So that's kind of like a hard merit question, really. You need to understand when you have a cubic equation of the form x cubed equals k cubed, like we did in blue there, that it's got 3 solutions and they're all equally spaced around the origin. The thing about this problem is it gave you the solutions and asked you what the equation was, which definitely made it trickier. Okay, and then the last thing it asks us to do is to find the roots of the derivative. So fortunately we've got a nice format for p of x, so differentiating it isn't too bad. P dash of x, we can use the product rule. Differentiate the first term, and be careful of this because the k is a constant, so the derivative of the first term is 3x squared multiplied by the second term, and then differentiate the second term and multiply by the first term. Okay, I must say when I did that the first time around I left the k's in there by accident, and when you differentiate them they disappear. Okay, then we've got 48 x to the 5, 3k cubed, and another minus 24k cubed, so minus 21k cubed x squared equals 0. Yeah, solving a power of 5 equation is not bad if all the terms cancel, so we're factoring out the x squared out of that. 48x cubed minus 21k cubed. So x is equal to 0 is a repeated solution. And then the other three come from solving 48x cubed equals 21k cubed. Well, x cubed is 21 over 48k cubed. And we do the same thing as we did before here. We cube root to find the first solution. So the real solution would be the cube root of 21 over 48 times k. It might help to actually find that out as a decimal. The question asks us to sketch this on the diagram, so that comes out to be approximately 0.759 times k. And then the other solutions are going to be equally spaced around the origin again, because this equation here is one of those ones, x cubed equals a complex number kind of style. So 0.759k, if we go back to the diagram, is somewhere about there, and then the other solutions are going to be there and there. And in the exam you should copy this diagram into your answer booklet so that it can be marked. Catch you in the next video.